The second speaker today is Dr. Jim Webber. He is Neo4j's chief scientist and visiting professor at Newcastle University. At Neo4j, Jim works on fault-tolerant graph databases, graph databases, first and second edition, and graph databases for dummies. Prior to Neo4j, Jim worked on fault-tolerant distribution systems, first at Newcastle University, startup Arjuna, and then for a variety of clients for global consulting firm ThoughtWorks. Along the way, Jim co-authored the books Rest in Practice and Developing Enterprise Web Services, an Architect's Guide. Jim is active in the software development and database research community, presenting regularly around the world. So today, Jim's going to discuss graph data science and graph machine learning for the uninitiated.
Super good. So hi folks, my name's Jim. I'm a computer scientist. As Mark said, I work at Neo4j, the graph database company. I'm not a bioinformatician, I'm not a medical researcher, I'm not even a data scientist. In fact, a few days ago, someone called me a classically trained computer scientist, and I'm beginning to think that that was an insult. So I'm going to talk about the kind of computery parts of this rather than the bio domain, because it's the bit I know about, and I don't know much about drug discovery and biology, but I can help you by showing you some cool tools that might help you in your day jobs. So in particular, I'm going to talk about the kind of modern tech behind knowledge graphs and graph data science. So if that sounds attractive, let's get stuck in. So think about the last job change you made. Did that opportunity arise from something you already knew? Hopefully there's an element of merit and skill that enabled you to kind of traverse the career graph and find yourself a cool new job. But often it's not just what you know, it's who you know. So someone probably told you about an opportunity, and it's increasingly important to know where they are in the graph. Graph theory is amazing. Several hundred years old, came from a Swiss fellow named Leonhard Euler, originally designed to minimize the amount of legwork the Emperor of Prussia needed to do to get around the town of Königsberg, now Kaliningrad. Fast forward a couple of hundred years, and graph theory has become the bedrock of modern data science. And there's a bunch of research around this across many domains that can show how graphs how graphs can be used to solve very complicated problems very well. And one of the reasons why is that network structure is highly predictive. Here you see a graph, and you can clearly see with your kind of clever inferencing human brains that nodes A and B in this graph are unusual, right? In fact, they provide a bridge or what's called a weak link in graph theory between two components, two subgraphs. And when when some folks looked at the research around people, they found that these misfits, these organizational misfits, A and B in this case, tended to get higher pay and more promotions because they were the confluence, they were the vector across which information flows between teams in an org. So they have what's called higher betweenness centrality, and betweenness centrality is just one of many characteristics of graphs that can be mined for useful information. So what's even more interesting about A and B here is that these folks aren't necessarily the highest in terms of productivity, but when they're on teams, the productivity of those whole teams are higher. So graphs are cool and weird. And what we think is that relationships, connections between data are the strongest predictors of behavior. So there's a really cool book called Connected by Fowler and Christakis. And several years ago, I had the pleasure of meeting Fowler. And Fowler is a clinician, and he works on public health. He, in particular, is interested in the spread of pathogens. And one of the favorite pathogens that he studies is smoking. And a weird thing he found out by studying this through a graph theoretical lens is that smoking is transmitted at depth 2 in the graph. That is, if you smoke, you don't necessarily make your immediate friends smoke, but you make your friends of friends smoke. And I thought that was an astoundingly wrong prediction. But of course, Fowler and Christakis have the data that back this up. And through this graph theoretical lens, they're able to craft a bunch of public health tools in order to help stem the flow of smoking, obesity, and so on. Now, in their time, they were using old-fashioned relational database technology, which seriously limits their graph size. But in modern times, you can build huge graphs and analyze them. Our premise here is that you can't analyze what you can't see. We think that it's painful to engineer graphs out of tabular data sources, out of documents, out of tables or columns. Graphs are built on relationships, so you should store them appropriately. We're not alone in this. There is industry stalwart here, Gartner, who are really saying quite strongly that modern data science is predicated upon graphs. We see this here at Neo4j. We see an absolute explosion of interest in Neo4j's graph data science stuff. We have a graph algorithms book, which you can download from our website, that has 250,000 downloads now. In 1 year, we had 4 times the amount of traffic to our graph data science toolkit, and something ridiculous now, like about 6 million views on the graph algorithms video. So people are finding these tools really helpful, and they're embedding them in their workflows across a variety of industries. Now you get the sense I'm pretty excited about graphs. So this is about knowledge graphs. Let me recap what a graph is. It's not a bar chart or a histogram. It's a network. It's a network of things connected to other things. And this is a really easy data model. So here I've got a kind of social network sort of thing. You can read this again with your human brains. This is a very natural representation for you to read. You can see here I've got a node labeled Andre. He has a birthday back in the 70s. Peculiarly, he tweets at Dan. That's allowed. And you can see that there's some relationships connecting Andre to other nodes. So you can see if I follow the outgoing relationship labeled sister, I find another human. I find this person called Mika. And by the way, if I traverse from Mika leftwards, I find Andre is her brother. And you can also see there's other things in this graph that aren't people. So I can see that Mika owns a car. It's a Volvo, and that's because Neo4j started in Sweden, and we do like to mock our ancestry. And Andre drives that car, so Andre's obviously scrounging that car. This is a really simple data model. For any of you that have studied things like relational databases or RDF and semantic web, those things are really, really quite rich and difficult models to learn. This is it. This is the data model that modern graph databases use. No RDF, ontologies are optional. We just focus on getting stuff done. And it turns out this is a really useful model for a wide range of things. Yes, networks of people. We've seen networks of people in the social networks, Twitter, Facebook, and so on. But also we've seen things like transaction networks. We've seen, particularly during the pandemic, we've seen things like supply chains collapse and reform and so on, and that's a graph problem. Importantly, for the purposes of this talk, knowledge graphs or knowledge networks are everywhere. We've seen enterprise content being cataloged through enterprise knowledge graphs, and we've seen things like NASA be able to rein in all of its internal knowledge and figure out actually a way of getting us to Mars 2 years early by relying on information that they found through the knowledge graph that came from the Apollo program. So we've seen graphs of IT infrastructure, clinical pathways, flight paths, drug recombinations, Mars missions. So many things can be conveniently represented in a graph, including plenty of bioinformatics use cases as well. So our view of graphs and data science is this kind of intersecting set. And I do appreciate the irony of using a Venn diagram when I'm meant to be talking about graphs rather than sets. So forgive me, this is the only time I'll do it. But we think there's this kind of interesting kind of overlap of things that are happening. We have in one corner, we have this emergent world of machine learning, which is now super popular amongst computer people and domain users. We have this idea of data and queries that we want to run, and that overlaps with machine learning insofar as we can drag features for machine learning out of our data via querying it. We also have the kind of human side, visualization. So we have tools where data can be visualized so that clever human brains, which are still needed, we can't do everything via regressions or neural networks. We have clever humans looking at the data and thinking, well, that's interesting, I'd like to know more. And there's an overlap there between visualization and analytics. And if you bring visualization with its data exploration, with queries, with the feature engineering, with machine learning and analytics, all that together gives us what we think of as graph data science. At Neo4j, we also think there are kind of levels of this, and the sort of steps of increasing sophistication you can take with each building on the previous. At the bottommost level, and that's not to say it's without use, in fact, it's tremendously useful, are knowledge graphs. And knowledge graphs are graphs onto which you have imposed some organizing principle so you can make sense of that data. And that organizing principle can be really simple, like the graph I showed you a moment ago with Andre and Mika owning a car and so on, or it can be sophisticated. You can take complex taxonomies or ontologies and impose them onto the graph. But importantly, once you see through the lens of the organizing principle, you know how to organize and interpret your data. That alone is very useful. You can run sophisticated analytics and queries on just a knowledge graph and find out stuff you didn't know before. But that's not the end of the story. We can then take a step up to graph algorithms and let the machinery find things for you. Find clusters of nodes, find busy paths, find important nodes for you without you as the human or the query writer having to do that stuff for you. Those of us from the computing science background, we think of these as graph algorithms. That we were probably taught dozens of them when we were doing our computing science undergrad. But these unsupervised machine learning techniques allow you to identify associations, anomalies, trends, all sorts of stuff without you having to kind of laboriously do that for yourself. So the machinery takes the strain for you. And at the top of this kind of hierarchy, or at least today, the top of this hierarchy, we've got graph native machine learning. And what we're doing there is we're using embeddings to learn features in the graph that we don't even know. We're actually encoding the topology of the graph for downstream model training. We can also detect missing labels, missing links in the graphs and so on. So we can solve the kind of canonical problem in graph theory, Zachary's Karate Club, really easily. As an aside, there's an O'Reilly book on knowledge graphs that I wrote with some colleagues. You can grab that for free from the Neo4j website if you are interested. So what do we offer for folks to use? And I'll point out that Neo4j, although we are a commercial enterprise, Neo4j is also an open source company. So you can get all of this on an open source or for free basis for modest amounts of work. If you're wondering what the commercial angle is, if you need to scale it up and do this in production, that's how Neo4j makes its money. So I'm not necessarily trying to flog you anything. You're free to use this stuff. Download it from neo4j.com and have a play. But we see the end-to-end toolkit as being centered on the database. That's the center of our universe where graphs live. And then supporting that in parts of the platform, we have our graph data science library, which is a bunch of machinery and algorithms to process graphs, to do graph compute, and we've got a tool called Neo4j Bloom, which is a visual analytics tool. It turns your graph into a Google-style user interface where you can use Googlish or googly English to try to discover things that maybe you didn't know before, collaborate and share with your colleagues, so that you can then put them forward for further processing. And that further processing is done in the Neo4j Graph Data Science or GDS library. This is about 70 odd graph algorithms and machine learning methods, and highly parallelized, incredible bit of computer science that went on here. Scales to tens of billions of nodes and rows in memory. It's lightning quick. And the way it works is that we have this kind of analytics workspace. You do a projection out of your database. You create a computational graph of some elements of the data you're interested in investigating, and that lives in what we call the graph catalog or the model catalog. And from there, then you can choose to run one or more of these data science techniques, these graph algorithms. So you can start to iterate over that model and start to look for insight, to tweak parameters, to tweak your algorithm choices so that you can get insight into the data that you've projected out of your knowledge graph. And for those of you that have experienced graphs before, that the headlines here look, I hope, pretty familiar, right? There's pathfinding, there's centrality, there's community detection. There's link prediction, there's even similarity, and more interesting or more modern things like graph embeddings and supervised machine learning. So it's a very rich library, and what's more, it's trivial to use. You don't need to be a database expert to use these. It's a very simple workflow. So as I said, our special source we think of is the graph catalog, and this is an analytics workspace, a data science workspace that enables you as a data scientist to effectively run experiments. Neo4j automates all of the data transformations and enables you just to get on with your work, and it's designed for fast iterations and layering. It's also production ready. This has been battle tested now for several years. It's ready to go. And what's nice about this is when you find something that's successful for you, a projection of the graph that's useful with a combination of algorithms, you can persist and version that data, so you never lose any of that provenance stuff. So how's this going to help my ML project? Well, how I think about it is that we have a kind of bifurcated world. Neo4j will provide you out of the box with a bunch of unsupervised graph algorithms. So these are for things like clustering, community detection, centrality, so you get page rank and all that kind of stuff. And we also get some supervised machine learning. So we can ask the infrastructure to predict how a graph will evolve, how links will appear in the graph, or indeed how a node should be classified. And I've just recently been working on some stuff around that, where we actually classify nodes as normal customers or fraudsters. It's been quite an illuminating thing. So you don't really need a huge amount of computer science skill to do this. You simply need to know your intent and how to pick an algorithm or technique that will allow you to achieve that. But we can do more, right? In fact, you can already make better predictions with data you already have. When we hear from data scientists, they tell us that if they just had more features within limits, that they would give you better models. But that's often not feasible, or they just add the same type of information. It doesn't at all improve results. But instead, if we add in relationships, network structure, that topology stuff that's hiding in your data, you kind of get to double dip. You get to extract more features out of that data to build better predictive models. So why not, out of your graph, add PageRank, add centrality scores, even encode the topology using node embeddings that we saw previously, and add that into your machine learning pipeline. And you can use those features to increase accuracy. Furthermore, you could even start to have predictions not only influenced by graph structure, the PageRank, the betweenness, and so on, but you can move over into making predictions about the graph structure. So you're filling in the links in the graph here, or the machinery is filling in the links in the graph here, just like back in the 70s Zachary did with his karate club. But you can also then go on to do node classifications in the graph without having to do any complex ETL jobs or any kind of plumbing work, which just gets in your way in your day job as a data scientist. So we think of this as graph feature engineering, right? So we take graph features out and we use them to improve classifiers, or we add columns effectively. But instead of running multiple algos to capture specific aspects of graph tech, you use embeddings instead. So this is nice because you can learn a representation of what's important in your graph and encode the topology as a feature into your ML model, which should have the impact of improving your classifier, making it better than using just plain old columnar data. If you want to, however, do this in the graph, if you don't want an external pipeline, you see the graph as the center of your world, you'd like to enrich that knowledge graph, we can, of course, ask the database to classify nodes or predict links for us. It's actually straightforwardly possible inside Neo4j. The graph is already labeled data, relationships have types, nodes have labels on them. And so asking the machinery to kind of fill in the blanks is relatively straightforward. In fact, it's so straightforward that all you need to do is call one procedure from a Cypher query, and Neo4j automates everything else for you. It splits train and test, it builds the logistic regression models with the training data, it evaluates the accuracy of the models, and it returns the best performing model. It's really straightforward. As I said, I'm a classically trained computer scientist. This should be out of my depth, but with Neo4j, actually even I can do this. And the same thing applies to link prediction. Neo4j automates all of the tricky parts of enriching the graph with additional links. So we call a single function, we train on it, and then we have a predictive model in the catalog ready to apply to new data. So we handle all of that ML ops stuff for you, freeing you up to do the important stuff, which is the graph data science. So in terms of zooming out, in terms of machine learning models in Neo4j, you train a model using your graph and you apply it to new or unseen data. It's no longer just a data model, much as I love data models, but it is now a predictive model. And those models live in the model catalog, and it has all of the provenance information that you need as a scientist to make sure that you're not losing anything, you're not losing fidelity as your experiments proceed. These trained models can also be persisted to disk, so they're in theory safe forever and shared with colleagues. So we want to foster that collaboration as part of your graph data science workflow. In terms of the overall workflow, very straightforward to think about it. So we have the feature engineering stuff. So we've got queries, algorithms, and embeddings that are generating features for us. We then get to train a predictive model. Then we either store that model in the model database, or we move to applying that model to existing or new data. And we can also, of course, rehydrate stored models from the database there. Once we've got a model, we can then straightforwardly use that for predictions and decision making, or we can use that predictions to enhance the graph, which is something I particularly like because we get feedback back into the original graph, which enriches it and makes it better the next time we use it. And then ultimately, finally, we can also publish and share that model for collaboration with our colleagues. And this all integrates with everything that you work with. So we integrate with a whole bunch of other data sources. We integrate with a whole bunch of ETL tools, streaming tools, and so on. If you are working in an organization where you have kind of nerds like me around to plug stuff in, all of this stuff plugs together really nicely. So you can bring all of those data sources into the graph. You can treat it as part of your knowledge graph and do some really advanced stuff with it. So in terms of use cases, loads of people are doing this. I've picked a few for this. Boston Scientific and AstraZeneca in particular. And Boston Scientific's problem was supply chain. They build stuff that scientists use, and they had difficulty finding faulty components in their supply chain, which was really hammering not only their ability to make money, I guess, at the bottom line, but also kind of jeopardizing the reputation of their instruments, which of course they can't have. We need to have calibrated instruments that we can trust. They've used a knowledge graph to model and analyze their complex products. So how have the effective bill of materials for each product across a wide range of products. And then they're able to really rapidly pinpoint root causes of problem, effectively common ancestors that could be causing problems. And this has reduced query times from over 2 minutes actually to a few seconds, so they can spot problems in their supply chain quickly. And I think of this as kind of an anti-recommendation, which is, hey, don't use this component or this batch because it's causing problems in the instrumentation. Fraud is another one that's been with us for a long time, or in general, finding bad actors has been with us for a long time. So this was a graph data science use case, and they fed in a graph of transactions and customers, and they built a predictive model based on the graph and based on graph features. When they ran that model, they actually, this large bank in the US, identified millions of dollars of fraud in the first quarter of operation that was previously undetectable, where they, of course, they had ML stuff in there before, but they didn't have the rich the graph features that come with having your data stored as a graph. AZ have been doing some work on patient journey, and their insight is that no patient journey through the healthcare system, this was the US healthcare system, is the same, but they wanted to find places where they could improve outcomes for patients. So they really wanted better intervention for complex diseases, and complex diseases develop over many years, perhaps with many visits to doctors and other healthcare professionals, with tests and evolving diagnoses. And what they wanted to do is understand where this came from, the trajectory of a complex disease. So how to identify early warnings, how to intervene faster, and hopefully improve outcomes. But if no two patients are the same, the question arises, how are the similarities found? In fact, they did some work here. They did a kidney disease intervention project. So they had 3 years worth of visits, tests, diagnoses with tens of billions of records. This was turned into a knowledge graph, and we had graph queries and algorithms running over that graph. And they ran community detection to help find similarities over time. And they found influence points in the graph where experienced physicians were able to perhaps guide and assist. And where they're going with this is they're going to start to use path-based embeddings to learn the healthcare pathways of their patients, so that then in a predictive model, they can hopefully see early on in your journey that something down the line may happen that will not be good for you, and they can intervene in the process much earlier than they otherwise could have, which I think is very heartening. So look, we think graph data science answers the big questions. Connected data, graphs are extremely powerful, but traditional approaches, including those that kind of early attempts at graph from the semantic web, they kind of make it hard to do this stuff. Graph data science on modern graph data tech uses those connections to answer critical questions. I think that going forward, that's what we're going to see more of. That's the macro trend in computing that will trickle over into the domains that you're working in. Neo4j Graph Data Science is really good for this. The algorithm library is really rich. It offers graph native ML, and it's humane. Even classically trained computer scientists can run it. It's very scalable, so even for some of the large data sets that you folks are working with, it will work. It's extensible, so we can suck in data from other places where you've got it. And there's loads of friendly people working on this as well. The community around Neo4j is awesome. You'll always find someone that can help you, and you'll often find someone that's working, if not directly in your domain, then in a neighboring domain that you can have a meaningful conversation with. Before I finish just now, I'll just say there's a bunch of free ebooks. If any of this kind of graph technology stuff tickles your interest, head over to neo4j.com. You can pick up any of these books here for free. I wrote a couple of them. That's great. And have a go. So look, folks, thank you for listening. If you don't mind questions via email, happy to answer your email. But in a few moments, I am going to have to hop off for another call. It's my I have to go on a call with my boss, and he's quite insistent. So thank you for listening, and I hope to catch up with some of you folks in the near future. Back to you, Mark.
Hi, Jim. Thank you for that. That was a really interesting talk, and even as a sort of geneticist background myself, I sort of understood that. It's good.
Super, thank you.